All right, welcome everybody. Thank you so much for joining today for Designing Walls for Control of Air, Water, Thermal, and Vapor. Today's CEU course is presented by Ben Meyer and Herman Lopez from Siplast. So they're going to be presenting today's CEU course. This is AIA approved for 1 LU HSW. So we did ask for AIA numbers upon registration. I will also send over a little form shortly in the chat. So in case you're worried you didn't include it there, you can fill out that little form and we'll make sure to report your credits directly to AIA. My name is Bo. I'm with Acelab. We're helping out with hosting today's event. And my colleague Helen Lemus is here today. She's going to give a quick little intro about Acelab and how to use it for your product research, as well as how to find today's presenters to reach out to them after today's event if you have any follow-up questions. So I'll hand it off to Helen to get started with a quick little intro, and then we'll go ahead and get started with our CEU course for today.
Awesome. Thanks, y'all. All right. So I like to do this with a little bit of audience participation. So get ready in the chat. Is my screen share showing yet, Bo? Okay. Looks like now.
I believe it is now. Yeah.
Cool. Great. So in the chat, I would love to know, we're going to look for some windows here. So this is our homepage. We gave it a nice little update for the year. So what you'll do is you'll type in what you're looking for, select products here. So we're going to do a window search together. And then, like Bo said, we're going to finish with how to get in touch with manufacturers on Acelab. So this is the audience participation. Anybody want to select what kind of window we're going to look for here? You can put it in the chat.
The chat is the little Q&A box. Oh, we have somebody who raised their hand. Oh, they stopped.
Oh, okay. Well, then I'll pick for you. We're going to go with a casement window today. This is our product quiz. So as y'all go through, you're going to see the steps that you're in and the number of search results as well. You'd select the project that you're working on. That'll give us the location, which will be helpful for anybody and yourselves as well. Here we're going to select a frame material. I see we have some folks in Q&A. Oh, we did casement. Great. All right. So what are we looking for in terms of materials? We can multi-select here. Any thoughts? What have we got? Well, I'll go. What was that, Bo?
I was going to say wood or like aluminum clad wood, maybe.
Yeah, we'll go with both of those. All right. We're going to jump to the next question here. We're going to select our energy performance. I'm going to go with these two. Again, as we're going through, we can see this number of search results going down. Jump to the next question. This is anything extra. Maybe we're feeling very green right now. We want to do passive house certified. We'll go to the next one here. Skip and show results. And so this is going to show y'all all the results that match those criteria. You can go back, you can adjust this. You can save these, and we can talk about how to use this more on a demo if you're interested. But then the other thing that I want to share with you is once you've made these selections, you're able to reach out directly via using Acelab to folks like Benjamin and Herman here. So one way to do that is you can come up here, select brands, type in who you're looking for. So type in these guys, and then you can go to their page where you'll be able to reach out directly to them for questions that you may have and see all of the products that they have as well on Acelab and just learn more directly there with them. So with that, I will pass it back. Thank y'all.
Cool. Thanks so much, Helen. We've launched a quick poll, so if you're interested in a short demo to learn more about using our platform, feel free to sign up for one. It's totally free, and Helen can help you out with all your product research needs. All right, without further ado, I'd love to pass it over to Ben and Herman to get started with today's AIA-approved course. Thank you guys so much for joining today. Feel free to take it away whenever you're ready.
Awesome, thank you. I appreciate it. So we'll introduce ourselves quickly. So I'm Ben Meyer. I'm the Building Enclosure Business Director at Siplast. My background is I'm an architect, and I've worked in enclosure consulting, worked for manufacturers for a number of years, and I've worked in real estate development back in the before times. So I've kind of done it from every position. So Herman, you want to introduce yourself?
Yeah. So my name's Herman Lopez. I'm the National Sales Manager for the wall control product offering from Siplast, which is all of our building envelope products for walls, including thermal, a couple of other product lines as well. But for the sake of our presentation, that's why I'm here. I've been in the industry for approximately 30 years, with about 18 of that on building envelope. So a bit of a building envelope nerd. I enjoy it. It's a lot of fun and always challenging.
All right, so let's get rolling. We have, excuse me, a bit of a cough, so if I annoy you, I apologize. It won't seem to go away. So this is a CEU. You'll get HSW credits for hanging out with us. and learning about wall control, controlling for design. Description, I think, is what got you here. We won't read through that today. Big picture, let's go right to the outlines. There's learning objectives and meets HSW requirements. And so for the outline, big picture, what we're going to go through is kind of an overview. Initially, we'll talk about control layers, and we'll kind of work through them one at a time to kind of work through air, water, thermal, and vapor. And what should you think about each one and how they combine? Then we'll get into some examples to kind of put that into practice. And we'll look at 3 different examples there. And then after that, we'll kind of back up and say, well, why does this matter? Where does this apply? And we'll look through some code requirements and some performance expectations and how do you manage that? And then we'll kind of just wrap it up with how to put it all together. So with that, I think we get started. Herman, you want to take it away?
Yeah, so when we're looking at the building enclosure, when I started with building envelope, we really looked at the 4 walls almost separate from the rest of the box, if you will. But I think as we've grown to understand the building science of the enclosure, we've understood that it's all 6 sides of the building: roof, fenestrations, whatnot, top to bottom. One of the reasons I like this graphic so much is, we're really going to talk about really just protecting the 6 sides of the box, or at least managing the different energies that can move through it. But I love this graphic here because even within a structure, you can have different environments which you need to manage. A ventilated attic next to semi-heated storage, adjacent to some conditioned space. Your strategy cannot just be keeping the outside out and the inside in. You actually have to take a look at it holistically and see the entire structure. Next slide. So when we're talking about the building enclosure, we're really talking about 3 different things. We're looking at the materials, basically what makes up most of the building envelope for the walls. We then need to tie that in utilizing accessories, whether it's tapes, flashings, sealants, and whatnot. And the third component there is just the components. You need to interface that wall. It's rare that we have a monolithic wall with nothing coming through it, no holes poked into it. So you need to integrate those first 2 with the components that are go into that wall, whether they be windows, doors, pipe penetrations, and whatnot. But the one thing that's missing from this is you can spend a lot of time working on these 3 things and really just bang your head against the wall to get it perfect. Where the rubber meets the road is the execution. So the 4th component here is when you're looking at the building enclosure, it's making sure it gets executed the way you want it to, and that the materials are being used in the manner that they've been designed for.
And when we get into the examples later, the sequencing will be a big part of that. How does it work? Can you build it the way you want it? That we'll talk about that a lot.
Absolutely. So the ideal roof, it's always tricky because ideal is a little misleading. I don't think there's a perfect solution. I think there's a perfect solution for the conditions that you're facing with the structure, whether it be geography, orientation, usage, and whatnot. But as we look at it, the strategies for these all really remain the same, which is managing those energies, keeping what you've worked to protect away from the unconditioned space. But whether it's a slab, a wall, or a roof, the management is really the same. One of the things that's going to come up later in the presentation is as you look at what makes up the ideal roof to wall example, managing thermal, water, and air. If you can manage those 3, you can take care of the vapor in managing those 3. And so as you're looking at those 3 different systems that manage those energies, you can take care of that 4th. So little food for thought, but we will talk about that a little deeper later in the presentation.
Yeah, and keep this ideal kind of as a frame of reference as we get into the examples, because none of them are going to be ideal, but it's a good frame of reference. Like, how can we get it closer? What can we do to kind of adjust as we go?
Absolutely. So when we're talking about moisture risks, we understand bulk water. I was just in New York this week, and it snowed pretty hard, and it rained pretty hard as well. And I was looking out my window, and we understand how to manage moisture because it's something we can see. It's tangible. It makes up the bulk of the moisture that your structure is going to see. But because we can actually see it and touch it, we can understand how to manage it and move it away from the structure. When you get into moisture vapor, it becomes a little more ethereal. It's a little harder to understand that because it's not something that you can see. There's humidity in all of the structures that we're in right now, but you couldn't at a glance know what the level of humidity is. So you need to work at managing that moisture. So if we were to look at vapor diffusion, if it were 99 or 90% relative humidity outside, which would be a disaster here in Colorado, but let's just say that it's 90% relative humidity outside, 10% relative humidity inside of my home. It takes a lot of energy for that moisture to move its way through the wall. So if we didn't have any breaches in our building envelope, you can manage that moisture fairly efficiently. It's not until you add air transport. So if vapor diffusion is 1x, with air transport, with a breach in the membrane, with inconsistencies in the flashing and whatnot, breaks in the system, if you will, you can get between 10 and 100 times more moisture moving through that wall assembly. And so as we look at it, as I mentioned before, continuity is going to be key in managing these energies, whether it's moisture, thermal, or air. And of course, bulk water, again, about 1,000 times more. So.
And so with that, it's kind of, an order of magnitude. How are we going to approach all these problems? That kind of frames that. So what we're going to do now is kind of look through each of these control layers. So we'll work our way through a water control layer, air control, thermal, and vapor. And at each level, what are we looking for? So that'll be kind of the component portion. Then we'll try to put those all together and look at some examples and say, well, what trade-offs are you trying to make as you go? So we'll start with water. So the first one, to Herman's point, water is, I don't want to say it's intuitive because we get it wrong all the time, but it's a little bit more obvious when you've gotten it wrong. You can kind of see, oh, the water's draining back towards the building. We don't want that. We want it to go the other way. So things like that are relatively obvious, but from a design perspective, you can design for them, knowing where you want your water to go on the roof. Do you want your coping to slope backwards or forwards? Those are important to understand. And then also, as you get to the building meets the ground, that the ground drains away. If you can get the benefit of venting or allowing any moisture that gets behind a cladding to dry back out, like that's going to prevent or limit the amount of load you have to deal with if there is a leak. So some of that is really just a matter of kind of risk management. And the last piece, and this is going to be a mantra through the whole thing, that vapor diffusion is really the last thing you get to worry about. You have to solve all the other problems first. And once you have those kind of sorted out, and you can say, all right, what is my vapor risk? Because to Herman's point, it's a very slow process. And at best, it's going to help you with drying in the case of incidental moisture. At worst, it's not necessarily going to be driving enough water through a system that cause immediate failure. There's something else going on if you have that amount of water. So
And the wall assembly is a little different. I'm sorry, I didn't mean to interrupt you, Ben, but the wall assembly is a little different in that when a roof has an issue, it at best shows you some staining on the roof that shows you ponded water, and you need to address the system, or you could even have some plants growing around the drain because the water has been sitting there so long, which I recently did see. In the assembly, in the wall assembly, when there is a failure, when there is moisture that's made its way in, especially moisture vapor through air infiltration, it doesn't present until a disaster is happening. If you have some organic growth on an area of the wall or some efflorescence happening on some masonry, you likely have a disaster happening on the other side, because much like it takes a while for it to get in there through diffusion, it takes it a while to present itself and let you know that there's a problem.
That's a good point. And from a water perspective, kind of saying in that lens, how do you specify that? How do you manage that? And there's levels of things you can specify. So specifying materials that meet water resistance requirements is kind of table stakes. That's basic, fairly basic. And a lot of materials will meet that. Assemblies go a little further, meaning that the manufacturer has also taken those materials, applied them in a fashion that should perform, and done some level of testing at a lab scale, putting two things together and making sure they work. So specifying, ASTM E331, this is water test, or these acceptance criteria that kind of demonstrate basic levels of performance, that's a good place to start as well. But the in situ, I mean, this is really what Herman's talking about, is does it stop the water the way we thought it would? And this is really what in situ testing allows you to do. And you can specify this, it can be part of the commissioning plan for a project, is how is confirming that you've designed it, you specified it, and it was built, and does it perform the way you intended or the owner thinks it should? And that's really, a very important thing to do. And you'll see this repeated really through all the control layers. So when we get into air, excuse me, air control, so moving from water to air, kind of working our way down orders of magnitude of risk and moisture management, air is a little bit more nebulous. It's a little less obvious than water. It's hard to know, you know, you're not looking for drainage and drips, you're looking for continuity. And a lot of times the continuity is only really obvious while it's being built. After the building is finished or clad, it's hard to tell, is my air barrier continuous visually? You have to do some other things. But it is required, and it is also the responsibility of the design professional. This shows up in the energy code. This shows up many times. That responsibility for continuity really relies on the designer of that structure, and that's called out in the IECC section. It's also called out in ASHRAE 90.1. And just like with water, there's lots of ways you can specify that. And the Air Barrier Association of America has helped a little bit. They add kind of a layer of evaluation on top of this, where there's material tests to say, hey, does this material stop air? It's a good place to start. There's assembly tests. When I put two things together, does that connection airtight? Does it perform as intended? And there's some stress that they apply to it. But there's also whole building air tightness. This is really the in situ test to say we designed it continuous. We spec the right materials. The question is, did we build it correctly, and is it performing? Are we going to get those energy benefits and those moisture saving or moisture reduction risk benefits? And that's where the whole building air tightness test comes in. Becoming more and more required by code. There's a certification program through the Air Barrier Association. This is really driving the industry forward because it's, again, visually you can't see it. You can't go out with a checklist and say, oh yeah, there it is, it's all done, I made sure. You really have to stress test the finished product.
And you know, that situational testing, it's not a test of as much about the details or even the materials used. It's about the craftsmanship. We do quite a bit of it here in Colorado, and it came up quite a bit in New York because I think we're starting to see, to your point, Ben, bigger and bigger pockets where whole building blower door testing is being requested either by code or even by owner developers. It's a test of the craftsmanship. And having been on a number of these projects, there's a lot of nervous people in the parking lot when these tests are being done, because you're really being graded by the people you've put on the project.
Yeah, that's a great point. And thermal control looks a lot like air control in that it's required for, continuity. It's a design professional's responsibility. It's a little easier to inspect. It's there, it's not there. Many times the questions for thermal continuity comes from, where do I need to insulate? What are the requirements? Sometimes there's some ambiguity around that. And we'll get into that, a little bit of that with the examples about where, when, does that count as a thermal bridge, all those things. But part of it is, a lot of these materials are rigid. They're kind of board materials. And so designing for thermal movement, what do you do, for continuity to make sure that everything stays connected is a bit tricky as well. And similar to the air barrier, there's a requirement for depiction of where is the thermal envelope and what are the requirements in the design drawings in the project set. And why does this matter? We talked about continuity. So we'll jump around a little bit on this slide, and we'll also go through we'll break it down in the next section. So what you see on the right-hand side is two thermal images of basically the same parapet, but insulated in different ways. The one in the middle to the left is the insulation comes on the roof deck, goes around up the parapet, around and back down. And what you see is the interior space is really being excuse me, semi-conditioned into that parapet. The parapet itself, that cavity, is not really interior conditioned, and you can really get cold air that goes up into that parapet space and cause condensation, which is really what you have on the left-hand side. So this is continuously insulated, but the more and more that parapet gets separated from the interior space, the more risk you have of that moisture that maybe is interior generated from pools, cooking, showers, what have you, hitting a cold surface and condensing back down. And the one go ahead.
Go ahead. I'm sorry, but having shown this slide to a number of contractors, the question of constructability always comes up, and I always toss it right back at them and say, well, what'll it cost you to go back and fix it? Because you're really asking for a problem if you don't address it while you can see it.
Yeah. And what you see on the right-hand side looks a lot more like that ideal situation where the thermal continuity has been more continuous. It comes straight across and straight back down. And what you see is an improvement both in thermal comfort. So that red on the interior goes right up to the insulation. It doesn't ever get cooler at the edges, but it also reduces your condensation risk. So there's some other challenges that come up, like how do we attach it? How do we build it? How do we get our light frames contractor to stop building, put some insulation in, and start building again. So all those are different challenges, but it's really a matter of, for long-term performance, is kind of coordinating that worth the effort. And so, in the last one is vapor control, and again, this will be something I repeat over and over again. You know, if you're worried about vapor control or what's the perm rating of a product, you really have to solve all the other portions first. It's kind of the last thing you need to solve, because everything else is going to dictate, you know, that every material is going to have a thermal or a vapor profile in terms of, is it a vapor retarder or is it not, even if it's not in the product's name. And so really the challenge is like avoiding unintentionally placed vapor barriers, that you selected a material maybe for the insulation or the air barrier that has a vapor profile that may not be beneficial for the design. So trying to kind of balance that back out again. I will say, so there's a question in here in the chat around air sealing. You know, it's kind of a false dichotomy of air sealing, energy efficiency, and ventilation. Really, like commercial buildings have to have a unique and distinct ventilation strategy, and really having a better airtight building allows the ventilation strategy to actually perform as intended. So if you have a leaky building and you try to employ a ventilation strategy, you know, the leaks in the building could overtake or shift the design. So really providing a tight building enclosure allows a ventilation strategy to actually be effective and perform as intended. So that's kind of a constant, you know, I don't want to say trade-off, because it's really a false dichotomy. You really need both, and actually to control the interior environment well. And so from a vapor control perspective, all materials have some permeability or non-permeability to them. So it's really a matter of understanding what materials you have in your assembly, and is it designed to be vapor impermeable? And if it is vapor impermeable, is it causing a problem that you might not expect? And there's lots of ways to kind of figure out if it's causing a problem. There's woofing modeling, there's kind of best practices, but kind of going through that again as the last step, it allows you to kind of work through the specs and material properties without having to redesign the whole thing around kind of the tail wagging the dog, if you will. Because I will say most times when people are worried about vapor permeable or non-permeable, what they're really worried about is condensation. Am I creating a condensation risk? Am I going to get some moist, warm air hitting a cold surface somewhere, whether it's from the outside or the inside, and creating moisture and rot potentially into the future? So condensation and vapor permeability are actually two very different things. And one of the best ways to control condensation is actually with an air barrier. And we'll go through a very quick kind of scenario, and then we'll also that'll lead us to our examples. So when we talk about condensation control, we're kind of turning moisture in the air into moisture in real life, if you will. A lot of that happens from air movement, air moving from one place to another. So some of that is air leakage from the outside moving to the inside, which is infiltration, or vice versa. Air leakage from the inside moving to the outside is exfiltration. Or it can also happen what we call air intrusion, which is air kind of from the inside of the space, is what we saw in that parapet earlier, moving up into a place that it really wasn't designed to go. Maybe it gets past your insulation, it goes up into a parapet cavity, but it doesn't leak. It doesn't leave the building. It just deposits moisture, then it comes back down. So all of those kind of improving our ability to kind of speak about what risks we're trying to manage is going to help us design it going forward. So in this kind of quick example, when we talk about condensation control, if I want to stop condensation, adding in vapor retarding materials may or may not help me. And we'll go through this kind of quick example, because everything highlighted in green in this very simple kind of roof to wall parapet scenario has vapor retarding properties to it. All of these materials can slow or retard vapor movement. One of these products has a vapor retarder in the name. That doesn't mean it's the only one. Like, so the self-adhered vapor retarder in your roof system, if they use it in the name, but it doesn't mean that it has the exclusive ability to stop vapor. So we'll go through a scenario. So in this scenario, we have the roof membrane. It's acting as our vapor retarder. It's an air barrier. And say we've done a great job and we've tied that roofing membrane all the way around the parapet, connected to our air barrier in our wall system. Does this stop condensation? And so in the scenario we looked at before, if there's air intrusion from the inside of the space that's carrying moisture along and it's able to hit a cold surface, I mean, getting up into that parapet, then we may still have condensation, regardless of the continuity that we created with the air barrier. So it can help. We're not getting bulk air coming from the inside or going to the outside, but we still have the ability for cold surfaces to be part of that moisture risk. if we move that air barrier down a little bit, so we use that self-adhered vapor retarder, not just as a vapor retarder, but it's actually part of the air barrier system. So again, we're not letting air pass that layer. If it helps a little bit, right? We've moved it down, it's below the insulation, it can't really get past the insulation, but we still have the possibility for it getting up into our parapet. If that's a tall parapet or if it's a very cold environment, the top of this parapet can be pretty cold. So we have the ability for it to moisture from the interior kind of staying on the inside, but hitting that cold surface and then staining the inside of the wall. And you see that many times below parapets where the kind of, it's a little bit of a rain factory in some climates if you have a very high moisture load on the inside and a cold parapet up above. And then the last one, kind of working through this in this logical way. If you really want to stop condensation, you want to make your air barrier look as close to that ideal scenario we talked about initially as possible, where it comes across the roof and turns straight down. The challenge with that is you have to essentially plan for that. You have to build that along the way while you build your parapet, make it continuous, and fill that space. And so in that way, any air leakage is limited with your air barrier, and any air intrusion, so interior moist air that wants to go past that and hit a cold surface, really doesn't have a cold surface to hit. It's all been conditioned and maintained inside the building.
And again, Ben, just short circuiting this type of situation, all the planning in the world isn't going to do you any good unless the execution is done correctly. So again, a qualified installer who knows how to manage those details and execute it correctly is a cornerstone of getting this done right.
Absolutely. So that was kind of a warm-up example. So we have some meaty examples we'll go through here, but this is kind of a way of thinking about what am I trying to manage? What are the risks I have? So we'll have a few example conditions. We're digging into I like to call the KCO study junior high. So we're going to look at three conditions, and at each condition, we'll look at kind of a 3D of the area. We'll kind of walk through control layers and what the risk is, what the design is. And then we'll also look at, to Herman's point, at the sequencing. How do the trades need to coordinate themselves in order to actually execute the detail? And I know from a design perspective, people early in my career, they'd say, well, that's means and methods. We don't need to worry about that. And I would argue if there's a performance implication, it's beyond means and methods. If you do it one way and you get one performance, you do it another way, you get a different performance. It's not means and methods anymore. You're actually implying, you're changing the outcome. So we'll look at a few of those. All right, so here we go. So this is our junior high. We're gonna dig in. We're gonna start right here. We're gonna start. I'm gonna call it simple, but it's as close to that ideal condition as we started with, where it's a flush edge, roof to wall. What you'll see as we dig into this is that it's not the ideal condition, right? It's close. It's about as close as you can physically do in the real world, but in order to enable the flush on the outside, it's never flush on the inside, just for structural reasons. So we're gonna dig in here. So this is the cutaway. This is what we have. So what do you see on the wall, Herman? I'll let you start us up the wall, and I'll take it to the roof.
Well, as we take a look at our condition, if we start at the base of the wall and work our way up, we've got a masonry wall with our brick ties. So obviously there are some concerns with thermal bridging. You've got to take into it. We're punching holes in our insulation, so we need to make sure the installation is done well. We've got our weather barrier over some concrete block. As we make our way up. And one of the keys, and it's funny because it's the wall and the roof kind of together. We've got a gutter that's up there that needs to be managed because, again, going back to our management of moisture, we understand moisture, bulk water, and we understand how to do it. But discontinuities in the gutter system is something I see all the time.
Yeah, so working our way kind of up and over to the roof. And what you see, and we talked about it being kind of that close to that ideal condition. So it's flush on the wall to the roof. You have a nice corner that has the gutter. But in order to actually build that, the structure is not ideal. It's got a little bit of a bump up where the bond beam comes up and creates room for all that roof insulation. So we have an adhered single ply on a cover board with insulation below that adhered, and then a vapor retarder down below. So this is a natatorium. There's a pool. There's lots of moisture on the inside. So we have a vapor retarder down at the deck level. But the key then is to tie that into the wall and make sure we're controlling as much to the interior as we can, because it's a pool and it's continuous source all year long. So let's dig into the control layer. So same detail. We're just kind of moving it to a 2D view so we can draw on it. Makes life a little bit more easy. We can see both sides of the wall here. So we'll start with the water control. You want to take us through that, Herman?
So as we look at the water control layer, really for the most part, we've got, are we moving that? We're looking at basically three different things. We're looking at the main water control layer, which is the roof, the drainage system, and whatnot. But secondary to that is going to be the facade. That's going to push away the bulk of our water and really get us ready for moisture management of vapor or the management of the vapor as it comes through. You'll notice that the building envelope is now to the interior here, or to the outside of the inner wall cavity there.
Yeah, and so, excuse me. So we'll move kind of to the, oh, I clicked away. There we go, to the air. So we have the vapor retarder down at the deck level on the roof. So we're going to use that as the air barrier. So it's a vapor retarder material, but if it's not connected to that air and water barrier that Herman was talking about coming up and over the CMU, then it's discontinuous as an air barrier. So to make sure we maintain continuity there. So it comes up the backside of that CMU and ties into that material. And it's also a vapor retarder there as well. And we'll talk a little bit about vapor retarder on the wall later on, one of the other examples, because one of the questions is, well, it's a pool. We should have a vapor retarder on the wall as well. Should it be an air and water barrier vapor retarder where you have the vapor retarder here on the outside, all in one, or should we do it on the inside here? And I think one of the things we'll talk about is really the risk of the moisture inside this space making its way all the way back through here. So you essentially would always have damp CMU. And is that really a strategy you want? Or are you going to lose bond to this material over time? So that's we'll dig into that a little bit later.
And Ben, I'm glad you brought up the issue of bond, because what is working now may not work in 10 years.
Right. And the last one is insulation. So at the roof level, we have 2 layers of continuous insulation at the roof, staggered and offset as it should be. And on the wall, we have continuous insulation on the outside. So again, protecting the CMU. And I have this purple here at the blocking for the parapet. And technically that's not insulation, but it technically also, if you look at the new thermal bridging requirements in ASHRAE 90.1, wood is considered a low enough thermal conductivity that you're not going to get a lot of R value out of it, but it's also not, letting a lot of energy escape. So wood is kind of that crossover material that's between insulation and not. All right,
but continuous wetting and drying is going to degrade that wood prematurely.
That's right, and so that's why you'll see like the air barrier and the secondary water resistant barrier is below that wood. So had this material come up and wrapped around, it would now be on the pool side, if you will. And that's not an ideal place for the wood blocking in this scenario. You really want that separated from the pool. That's a good point, Herman. Thank you. And so the last part we'll look at for the detail is really the sequence part. And this is kind of what Herman was referring to before. It's, we have the design, we have the materials. Well, how do we put it together in a way that is properly lapped, that the right person goes first? So we'll work through it. So from the wall side, we'll do the air and water barrier first. And then we'll do that piece of flashing that we just talked about that either separates the the blocking or connects to the roof system. And then we'll put on the cladding and the roofing material and tie those together so that they're lapped and sequenced in a way that actually protects it long term.
Ben, I always like to point out on this detail that integrating the building envelope to the parapet material takes a little bit of planning and strategy, because at times you're going to seal up that parapet before you put on that weather barrier, and installing the weather barrier after the fact, you may end up with a reverse shingle. Right. It just takes some planning, and it takes an installer who understands and trades talking to each other, which may be a presentation for a different time, right?
Yeah, and oftentimes this teal material is rare. Maybe is included in design, but not included in anybody's spec or bid. And they're like, well, I didn't provide that. I stop here, and I stop here, and there's a gap, right? And that can be a real challenge.
Yeah, if it's nobody's responsibility, it doesn't mean it doesn't have to be there.
All right, and this is a great example. They terminated. They run in continuity, and I feel like they were like 3 cap nails short of really sealing this thing off. What do you think, Herman?
Yeah. If one is good, 14 is better.
That's right. And so again, it's about, are the materials able to do what we're asking? It's easy to draw a dashed line and say turn roof membrane here, and I've seen some actually turn back and go along behind the blocking. that's the design intent. When it comes to the field, like, you know, 1 turn is kind of the limit on this material.
Then I saw an example similar to that had a release paper on the back, and they still use fasteners in much the same manner. And you say, you know, if you had just done it right, like you had all the tools to do it right, and it got it wrong, you know.
All right, so that was our first kind of detail. We're gonna increase in complexity every detail we go through. But let's move. So now we're gonna have a real parapet, you know, not just one that's hidden under the flush edge, and a roof to wall. So we're zooming in. This is on the gymnasium side. Got brick on one side. I think we might have brick on, no, just brick on one side, roofing material on the other. Do you want to walk us through the wall, Herman, and I'll take us around?
Yeah, very similar on the face. We're looking at a very similar condition to what we were discussing earlier. Masonry with brick ties. You know, obviously you want to make sure you manage any thermal bridging that's there. Make sure that you have continuity within the system. What makes this so complicated is that we now have a wall with exposure. You know, we had that beautiful flush edge that made it so simple because we keep the outside out, the inside in, and we know where those are. Here, outside and inside become a little more ambiguous. So as we come over the top, we've got some parapet cap there. We've got our wood coping and then our cap flashing, but we continue a wall on the other side. And so again, we're going to add some insulation, and we're going to bring a roofing membrane up to it. But the concern here is that we now have unconditioned air on both sides of it. We've got, it's going to be hotter or colder than the inside of the building, yet this wall is connected to all of that.
Yeah, and you can kind of see, as you know, on the back side of the parapet, and we'll look at the cutaway so you can see it more clearly. There's insulation on both sides of this wall, and then there's a built-up roof system, cover board, 2 layers of insulation, and again, a vapor retarder down below. And so there's a lot going on, and the fact that this is CMU might actually help us a little bit. If this was stud, we might have more challenges around managing air movement. But one thing you'll notice, though, is the first thing put on this wall likely is this piece of flashing below the parapet blocking, and that's going to do a lot of things for you. It's going to also protect the wall from filling with water while we wait around for the air barrier to be put on the outside, for the roof to show up, for the coping to be put on. One of the worst things that I've experienced is when you have these open cores of CMU for months, you know, it could be, you know, or just the wrong week when it rains that week. It can take a long time for that water to dry out of the system so that you get a dry substrate, because you have columns of water essentially inside your wall.
And
So,
Ben, it startles me how often I see somebody throw a fastener or two through the top of that cap flashing, and it breaks your heart because now we've got a breach in that protection that we were looking at.
all right, so let's go to the cutaway. Then we'll look at air and water. So I'm going to move a little quicker through this because there's a lot of repeat from the first one, but except for the wall. So from the water perspective, I mean, unlike the first one, we don't have a gutter. So in this one, the water's draining back to the roof drains, and so that it's collecting that way. We also have the brick shedding water, and then a secondary water resistant barrier behind the brick, behind the insulation. So that's any moisture that gets through the kind of porous brick, hits that and goes out the flashing through the weep holes on its way out to the building. From an air barrier perspective, so in this scenario where there's a vapor retarder down at the roof deck, and we're using the air and water barrier, the secondary that comes up behind, to tie that together for the air barrier. In this scenario, if you had done just the minimum and put the say the vapor retarder on the roof, turned up 4 inches, and then just started your air and water barrier on the other side, you would not have continuity in your air and water barrier. And there's even a question in the chat about kind of retrofitting a scenario like that. When we have essentially a CMU wall and the air barrier is not continuous, what do we do? Part of the challenge is, you know, getting back into it if they're solid cores versus not solid cores. Creating continuity in that scenario on the inside might be your best approach, but it's a tricky scenario if you don't get it right the first time, especially with a construction type like this.
And it's made even more tricky by how many trades do you suppose are having to work together and integrate everything?
Yeah, it's tricky. All right, and then vapor excuse me, vapor retarder on this one is just at the roof deck and turns up the wall and then transitions to the air and water barrier from there. Insulation wise, it has continuity. So we have insulation at the roof, We have continuity up the back side of the parapet, and we're actually using a cover board over top of that so they can attach the SBS onto that. You couldn't really go directly with the SBS onto the insulation. You need a separator, that cover board, for it to adhere to. And then you have insulation up the front of the wall. The taller this parapet wall gets, the more challenging this would be, the more you might want to look at essentially doing some vermiculite filled cores for a few courses and kind of making that separation there versus having, you know, lots and lots of insulation, not really conditioning the interior space, right? As that wall gets taller, it's not really part of the interior space. All right. And again, the same thing, kind of from a sequence perspective, this is probably one of the bigger challenges. How do we get it right? So again, working from the bottom to the top is the key, making sure you include scope to connect the two together. So from the air and water barrier to the roof system, and then providing either the cladding and the roofing, but making sure that they tie in a way that laps correctly and then is also well sealed behind. Because if the cladding shows up, if you have many times, if you have brick installed and you don't have that transition flashing put there, there's no easy way to make that connection again. You've kind of missed an easy opportunity. All right, we'll go through our third condition. And really, so this one's the trickiest of all, and it connects between the natatorium and the gym. So it's an exterior wall connecting two interior different condition spaces. So Herman talked right at the first slide, I think, where we have an interior space with multiple conditions, and how do we separate them? This is one of those cases where you really don't want your natatorium space kind of flowing, you know, down the hallway into all the other conditions. It really wants to be contained, so you can manage it and also manage the comfort in your gymnasium and the others. So this one, I promise complexity. I think we're bringing it here, Herman.
Yeah. You know, and on its surface, again, you know, we're assembling the wall components in a similar manner, but there's so much integration on both sides of this wall that have to be perfect the first time, because the danger that you have is the amount of moisture we're dealing with and the two different conditions that have to be separated.
So we'll spend a little bit of time kind of explaining what we have here before we go to the cutaway, because there's a lot going on. And here we'll add another image to show you the back side of the wall, just because it's hard to see in perspective, you know, two things at once. I don't have like the bug eyes. But so in this one, we have the roof system coming up and terminating onto a shelf angle. And that transitions to really just an exterior wall. We have air and water vapor barrier, insulation, brick on the outside of that. One important feature to note is that you see this is a two-piece flashing that terminates the roof. You know, I always joke that you can, you know, they could have saved probably $100 by making that a single piece of flashing, but it'd make it really hard to change their roof out in the future. So the fact that it's two-piece flashing lets them, one, have a continuous through-wall flashing, but also gives them access to maintain their roof into the future. So the little things can make a big difference. And then on the back side, it goes right into a roof system. It's on a higher elevation. It's a gymnasium. And so there's no brick or finish, but it is roof membrane on the backside with the substrate board. So let's dig into the cutaway on this guy. There, that looks complex. I think we have a lot to talk about here. Now, from a water perspective, on the natatorium side, if you remember, we actually have gutters. So this is all running this way out to the gutters. And then on the gym side, we have internal drains. So this is, again, running to the drain, and it slopes back from the brick to prevent staining. And we have a secondary air and water barrier here between the, really on the finished side of that roof, of the upper roof, transitioning to a through-wall flashing to the roof on the lower side, the natatorium. Air gets a little complicated because we want to keep the outside out and the inside in, but we also want to separate the gym from the natatorium. And some of this is going to come down to sequencing, like what's the best way? Are we actually going to build it with two structural elements? So is it going to be combined? If so, should we move the air management to the inside of the natatorium versus the outside? And I think these are the things that you go through in that process. Because really you want to maintain all the separate spaces and the separate, you know, total building enclosure.
Yeah, treating the gym and the natatorium as separate entities, and all the strategies following that is key.
And then insulation, and again, it's pretty tricky here. So we have continuous insulation at the roof coming up this parapet to the shelf angle. So this is actually pretty important. Lacking this shelf angle gets even colder. And if your air barrier truly does this and it allows the natatorium air to get into these CMU cores, you really have a lot of condensation. So this may be a reason to have your air barrier here on the inside and also a vapor retarder to prevent condensation from getting up into this system and showing up potentially as a leak on your gym side if it hits here. If you haven't separated those two, you have the ability for kind of warm, moist air to get all into this space and create staining and condensation, and hectic for your roofer who's trying to fix a leak that may not exist. All right, so we went through a lot of scenarios, and then vapor as well. So again, vapor to the inside, vapor and down the wall here to the inside to control, keep the natatorium to itself, and then on the back side of the roof membrane, but not here, not on both sides of this wall. We talked about giving the wall a path for drying. So this scenario where you're actually weeping out behind the brick, this side is really you want this to be vapor permeable, that you have a way that if moisture does get into the system, it has a pathway to dry out over time, so it doesn't kind of build and escalate and create all kinds of other problems.
Yeah, I think sometimes in our effort to keep moisture vapor out, we end up trapping some moisture in. Somebody I showed the slide to said, but if you do all of your work and you put a vapor barrier on both sides, you've kept all the moisture vapor out, not realizing there is some inherent moisture that's going to be there.
Yeah, and the pool is not helping your case any. Yeah, the pool is a constant source of problem. Like, so if you have a breach maybe in the paint on the inside of this wall, how are you managing that breach risk? And it's got to have a place to go. All right. And again, from a sequencing perspective, starting from the bottom, working your way up is key. So with this one, we're looking at the roof side. In this scenario, they're both roof sides. So you have the vapor retarder, kind of looking at that scenario where we have that air and vapor barrier on the roof side coming up and lapping over the vapor retarder from the roof. Then building your roof system, doing the through wall flashing, which is a two-piece flashing. So again, you can get to that roof later on. And then treating it as a through wall where you put in your flashing, build your brick on top of that, and then go along up from there. So again, that transition is super critical. It is super hard to get right, and it's a lot of trades involved from Herman's, as mentioned before. All right. And another fun photo. When you don't specify it, they got all the materials there. They just may not have it doing all the things that you want it to do.
Absolutely. You may have to squint to see some of the discontinuities here.
That's right. You could live in that one if you had to. All right, so let's keep going. So we'll go to codes. I think this is you get me for a few more minutes, and then I give it back to you, Herman. So just big picture. This is more, I just call it a reference slide, so that you can kind of come back to it. Because one of the challenges is that from a roof to wall, a lot of these requirements live in different parts of the code. I like to think flashing is the one thing that kind of bridges the two together. There's really the same requirements in flashing for walls as roofs. That any moisture that hits flashing needs to get its way back out to the outside. That's really the goal. But everything else is specified elsewhere inside the code. And the building code, the things in blue, don't always necessarily line up or refer to what's in the energy code, but they all need to be true, right? And that's why designers have jobs, because it's hard. If it were easy, if the code could do it for us, we wouldn't be here.
Ben, that came up quite a bit in New York this week, was contradictory energy codes that basically, to meet the energy codes, you're violating the building codes. And I actually had an installer say, "What do I do?" And boy, I don't want to answer that question, because the last thing I want them to do is say, "I built it this way and they told me that it's wrong."
Right. So this is a great reference. You can use this to kind of figure out what the requirements are. But the point is to kind of say that they're a little bit everywhere, and part of the design is to put them all back together again. In the same way, and this is more of I don't want to say a pet peeve of mine, but coming from the roof industry, I've worked in walls as well. That on the roof side, we really understand loads very well. We understand loads, how uplift and performance requirements, how many fasteners, where do we put the insulation. One of the fascinating things is all those loads exist and are calculated for the walls as well. We don't always apply them at the same level of rigor and uniformity. But this is really a diagram that comes from the ASC 716. For the same building, all of these loads are part of the same calculation. They come off of the same inputs. So if you're using different inputs for your roof in terms of importance and wind loads, and different inputs for your wall, you're not necessarily meeting the intent there as well. So be mindful of that they're all related. You know, I when I was in consulting, many times, many times, we would have, you know, locked in roof performance, and then we would say, well, if we just use a cheaper window, we can save a whole bunch of money. Is that okay? Well, the cheaper window doesn't meet the performance requirements in many cases. Like there's a reason it costs less, but we're not applying the same level of rigor to it.
Yeah, value engineering rarely takes a holistic look at the entire building.
So this is really a reminder. Go back to your structural drawings. Well, somebody's already done that calculation. Don't rerun it, and don't. If you need to go back, and you can, you know, question the assumptions, but it's going to apply to that whole building, not just the one thing that may be too expensive. And Herman, I'm gonna give it to you here.
Sure. So as we look at air and water barrier technologies, you know, we've actually we've reached a point where we're really forgive the pun, but pushing the envelope for what we've created as far as wall assemblies. You know, you look at butyl adhered membranes. Butyls are great because superior adhesion, excellent compatibility with materials. You know, I talk to specifiers all the time, and I always ask them, how much time do you spend while you're writing your specs validating compatibility of products, especially across manufacturers? I hear sometimes as much as 20%. You want to have products on the job that are going to be more compatible. It's how we got here. Because prior to that, we had asphaltic adhered products. You know, asphalt, for all of its attributes, can be a little tricky to work with on the wall assemblies. One, because of compatibility, the other because of things like leaching of the materials. As that product cures, it can at times kick out some of the material. It'll show up as like a brown ooze coming out at transitions at windows and base of wall conditions. Prior to that, we had mechanically attached. We had asphalt impregnated paper. We basically just took paper, added some asphalt to it, and stuck it onto the walls. And it worked. You know, our intention was good, but it was the wrong materials. A cellulose-based material and an asphaltic product that is going to dry out over time, not a long-term solution. So again, that's why we've ended up at the butyl adhered products. Same thing with the liquid systems. The modified silicones, the STPEs, the new products that are out there really have taken into consideration everything that we've talked about today. Air, water holdout, long-term performance, compatibility. Because prior to that, we had asphaltic solvent-based products. These are a little tricky, again, to work with. Some of the same problems that we have with the self-adhered membranes, but also because it's a solvent-based product, that solvent has to off-gas during the curing process, causing the material to shrink a little bit, sometimes, or I shouldn't even say a little bit, sometimes quite a bit. You can install an asphaltic material at 90 mils of thickness, and it may cure down to about 45 mils. Now, in the face of the wall, at the face of the wall, that's not really a huge concern, except for the fact that it's technically drying out, and you're kicking out, you know, potentially some VOCs away from the system, potentially going inside of inside of the structure. But along with that, the other thing is at the critical junctures, the transitions to doors and windows, seams, corners, and whatnot. That shrinkage can potentially cause some cracking, and those critical interfaces are the most vulnerable if you were to throw a crack in there. Prior to that, we had water-based. We had acrylics and emulsions, paints, if you will. They were a nice try, but they really were never at the time designed to work as a weather-resistant barrier. So again, as we move forward and as we expect higher performance from our wall assemblies, moisture-cured products like silicones, STPEs, they are definitely the way to go. So let's take, oh, we got a poll that just popped up. Let me get rid of that for a sec, because I want to continue with my slide here. So I'll move through this quickly because we're getting pretty close to the end of our time. But UV exposure. When we talk about UV exposure, we're really talking about two different types. Constructible UV exposure, as far as the amount of time it can be left exposed during UV, and extended UV, open joint systems, if you will. Talk to your manufacturers. Certainly the best is 6 months and greater. It doesn't take much. I just spoke to somebody in New York who said that they went 11 months with their product exposed to UV before they were able to cover it up because of some issues with the structure. So as you look and as you specify your products, make sure that you're looking at the UV exposure. Also, if you're looking at an open joint system, make sure that system was designed for prolonged UV. Some products may appear on their surface. They may have a beautiful opaque black finish to them, but they were never designed for that extended UV exposure. And again, I'll move quickly through here, but compatibility. You want to make sure products play well together. You want to make sure you're picking products and validating that you're not going to have any issues, both short-term and long-term. So high temp and low temp, again, I'll move quickly here, but testing doesn't always tell you the full story. I'll use just the example of ASTM D1970 there. Take a piece of wood, you angle it to 45 degrees, you put your membrane on, heat it to 300 degrees Fahrenheit, and if it doesn't run, it passed. Well, what you can't see very clearly in that image is that the HDPE top sheets on both of those disappeared. They shrank away. And in my book, yeah, I suppose it passed this test, but long term, especially behind metal panels, high heat conditions, we have a failure there. We definitely have a problem that's going to show up.
So yeah, just being mindful of how you specify, low temp for application, high temp for exposure, just really understanding that. And then I'd kind of let you go into this, Herman, sorry.
Yeah, so NFPA 285, very quickly. NFPA 285, for a lot of us, it's about as clear as mud, even on the best day. Understanding what it is, it's not a product test, it's an assembly test. So if somebody holds up a product and says, we're NFPA 285 certified, no, that's not the complete truth. What we're looking at is assembly tests. The three triggers there are the plastic foam insulation, the weather barrier, and the exterior cladding. The test itself is a pass-fail. There is no Class A rating for it. Modes of failure are propagation of flame to the second floor. It's a two-story structure, purpose-built, that they do the test on. Propagation of flame to the second floor is one of the failures. The thermocouples reaching 1,000 degrees at any time during the 30-minute test is a fail, or flames going 10 feet above or 5 feet laterally from the fuel source will cause that failure. There are some exemptions that are, there is an exemption now if the weather barrier is the only combustible component, but you need to design for that. So if you had a mineral wool insulation, a weather barrier, and masonry on the outside, you technically could get an exemption, but that product has to pass cone calorimeter testing and have a Class A rating. So again, if you come across NFPA 285, ask your manufacturers to assist you. We've done a lot. We do the testing. We can help you design that wall assembly.
All right, so we'll take you right to the end. I think we have 2 minutes left, and we'll hopefully get you right to the end. So, I mean, the goal of all this is to make your designs, even if you carefully work through, the control layers, that the design matches the reality, right? That's the goal. That what you design, you want to be built and perform the way is intended. And so, how do you do that? I mean, a lot of that is really, you want your drawings to be designed as continuous. You identify the materials, the transitions, detail them, specify them, and then also, if you need to, if it's a performance-driven, sequencing, then you have to kind of show what goes first. That it's critical that this element goes before the parapet structure. They're not going to figure that in the field themselves because that's not always the fastest way to build. And then from the specification side, you look for compatibility, request or require shop drawings to basically confirm back that this is my design intent. The shop drawings are them saying back to you, we understand your intent, here it is. And then define the scope, be clear about that. And then also have quality assurance and on sites, whether that's mock-ups, third-party testing, look for that coming out of the other end on the site. Yeah, kind of wrap, same thing, design for it, it's going to be tested. Enclosure is a system, it's all working together. And your specifications are important. They're not a request, or wouldn't it be interesting if, like, they're a requirement, so make sure that they're nice and tight and that everything works together. With that, I think we say thank you. Yes.
Beautiful. Perfect timing. Awesome. All right. Well, Thank you guys so much for a really amazing course today. And thank you everyone in the audience for joining us. I know we had a few questions. I think we got to most of them throughout the webinar, but we will have a record of those questions. So if anything went unanswered, the folks at Siplast can follow up with you after today's event. All right. With that, it's 2 p.m. So thanks again, Ben and Herman. Appreciate it. And I hope everybody has a great rest of their day.
Thank you, everyone.
All right. Bye.